In this section of Chapter 5, we will take a look at the Lewis structure and see how to determine the molecular geometry based on the Lewis structure. The molecular geometry of a chemical is probably the one most important part of that chemical that gives it functionality. That's so true, especially in the field of biochemistry, where the helical shape of DNA allows it to be able to replicate itself and also contain hereditary information. It's the three-dimensional globular structure of proteins that will determine its function or whether it's going to be rendered useless. So when it comes to the chemical world and its functionality, especially in terms of drug design and its potency, we need to pay attention to the structure of the chemical. In this particular slide, what you have here is the overlap of four chemicals, and it looks for the most part like just one structure, but if I unravel it, what you have here is codeine. Now, for those of you who are new to chemistry, what you see here is carbon, hydrogen, oxygen, and nitrogen. Here, where you see the angles, it's implied that that's a carbon atom right there. Carbon always has four bonds, so the fact that you see three bonds or three lines going to this carbon right here means that there's another bond that goes to a hydrogen, and that's just known if you're a chemist. Here there's two lines going to this angle, so that's a carbon, and the fact that you see two lines means that that carbon has two bonds, the other two has got to have hydrogen. Here what we have is a carbon. We've got 1, 2, 3, 4 lines going in, so that carbon doesn't have any hydrogens. So that's how you would interpret this line structure for codeine. So that's the structure of codeine. If we just pay attention to this part of the structure, what you have here is morphine. Now codeine is probably what some of you have taken in your cough syrup. Okay, it helps cough, it sort of helps pain a bit, but morphine is really the drug for pain. If you've ever been injured and you're in great pain, they give you morphine. And look at the subtle difference. If you take this OH group right here and you change it to an oxygen with CH3, also known as a methyl group, you go from morphine to codeine, a less potent drug, but nevertheless still a painkiller. Now if you take this basic skeleton of morphine and you change both its OH group to this is also called a methoxy group, methoxymorphine, dimethoxymorphine, you have the most lethal drug that man has ever invented. It's heroin. And heroin is a synthetic drug. You can't isolate it in plants. What you need to do is you need to take morphine and do a chemical transformation. And look at the skeleton that we leave behind. This chemical right here is methamphetamine. That's the backbone. That right there is methamphetamine. And you see that structural motif in all these drugs. So, when I tell you that the shape of a chemical determines its function, you can see that indeed it does so by these examples. Now, cocaine was a drug of the 80s. People would take cocaine because it gave them a very heightened sense of, it basically heightened their senses. And the way it did that was because of the neurotransmitter in your central nervous system in your brain. Usually what happens is that when you sense something, whether you feel pain or you have some sort of sensation, then these neurotransmitter goes from one dendrite to another through these pores. These neurotransmitters are small chemicals that fit in these pores nicely, and then they send an electrical signal down the line. But what happens is that when these things are uptaken by one nerve cell, then these neurotransmitter go back down to their original point of origin. What cocaine did or does is that once these neurotransmitters go up to these pores, it blocks them and puts them in. So this cell is constantly in a sense of excitement, you might say. This neurotransmitter doesn't have time to go back down, and so that's why their sense, uh, they just have a very strong sense of what's going on. Uh, these cocaine fits nicely along the DNA chain right here, or these receptor sites, and then clogs these neurotransmitters from going back down. Again, it's the shape of cocaine that does this. The way we smell is also triggered by the shape of chemicals. What we have in our nose, in the nasal cavities, are these sites where the shape of a chemical that is airborne goes up here. It'll give us a sense of pleasantness, like a flower or bakery, or an odorous sense. If it's the right shape, we might have we might think that we're smelling a cadaver because it's the chemicals that triggers this. So again, the shape plays an important role in terms of body chemistry. So, how do you determine the shape of a chemical? Well, we use this theory called valence shell electron pair repulsion. It's an extension of the Lewis structure. The Lewis structure, remember, we use the valence electrons to figure out how the atoms are arranged for a substance. Well, now we're going to use that Lewis structure to figure out how the atoms are arranged in three-dimensional space. So the whole idea of the valence shell electron pair repulsion is that the valence electrons repel each other because they're negatively charged. So they take on a shape that places them as far apart as possible because of electron-electron repulsion. Now, the driving force for this is the Pauli exclusion principle. No two electrons with the same spin can occupy the same space, so it has to go in a different molecular orbital. Based on that, you can figure out how many electron pairs are around the central atom. You can put it in something called an AE system, where A represents the central atom, okay, central atom, and E represents the lone pairs around the central atom. And if you know the AE system, you can use a chart to figure out the molecular geometry. Okay, so the AE system tells you how many lone pairs or how many regions of electron density are around a central atom. Now, if you replace some of these lone pairs with bonded atoms, what we have is the ABE system, where A again represents the central atom. Okay, the B now represents the bonded atoms. That is the atoms that are bonded to the central atom. Okay, so the B represents the bonded atoms, and the E represents the lone pair again. So these are the bonded atoms. And through the ABE system, you can come up with the molecular geometry. The AE system gives you the electronic geometry. The ABE system gives you the molecular geometry. And we'll discuss this in the slides later on. So let's take a look at the shapes of chemicals, keeping in mind that electron pairs take on a geometry that places these electrons as far apart as possible. So if you take a pair of balloons and you tie it, balloons like to occupy space, so they can be thought of like electron regions where these represent negative charge. So if you tie two balloons together, what you get is a geometry that places these two lobes at 180 degrees apart. That's the natural geometry. So this basically is what we call a central or a linear geometry. A linear geometry. When you have three balloons together or three lone pairs around a central atom, the natural geometry is going to be tetrahedral, and that's going to be 120 degrees apart. So it's tetrahedral planar because it's in a plane. If you have four lone pairs around a central atom, then you take advantage of the third dimension, and what we have is what we call a tetrahedral geometry. Tetrahedral geometry. The bond angle is about 109.5. We're not going to worry too much about 5 lone pairs or 6 lone pairs because that's beyond this book. But certainly you can, if you go into general chemistry, you would need to know how to do that. So the geometry that we are looking for in terms of just lone pairs or regions of electron density around the central atoms are these right here. We're going to be looking at linear, trigonoplanar, and tetrahedral. So how do we determine the shape of a chemical based on its Lewis structure? Okay, what we need to do is we need to pay attention to the central atom because it's the geometry around the central atoms that will dictate the shape. So first we use the Lewis structure. You need to know how to write a Lewis structure if you want to get to this part. Then we need to figure out the electronic geometry, and the electronic geometry is based on the number of electron regions around the central atom. Then we need to see how many electron regions are around the central atom, and that'll give us our electron geometry. Then we replace some of these electron regions with bonded atom, and that'll give us our molecular geometry. So these are the rules of how to determine the molecular shape. I will show you a shortcut. My shortcut starts with a wheel and a spoke. If you think about a bicycle wheel, which you see right here, you have a hub, and the hub is right in the center, and there are spokes going out to the periphery of this wheel that connects it to the hub. Atom, or a compound with one central atom, is kind of similar to this wheel. You have a central atom right in the center, and you've got flanking atoms, or atoms that are attached to the central atoms. But before you can attach atoms to the central atom, you have regions of electron density. And you can think of regions of electron density as spokes on a wheel. If you got one atom that's bonded to the central atom, think of that as one spoke. That's one region. If you've got two bonds bonded to, or three bonds bonded to an atom, think of it as a very strong spoke, but nevertheless a single region of electron density. So what you see right here are two regions of electron density. There's one region, two region, albeit the second region here has a triple bond, but nevertheless it's two regions of electron density. And then if you have a lone pair, that also counts as a separate region. So in order to determine the molecular geometry of a chemical, you have to count the spokes around the central atom, or the region of electron density around the central atom. So let's take a look at some example. Think of BH3. How many spokes are coming out of boron? If you say 3, you're correct. There's 3 regions of electron density in BH3. 1, 2, 3. How about CH4? That should be a no-brainer. You see 4. 1, 2, 3, 4. 4 spokes, or 4 regions of electron density coming out of carbon and methane. How about formaldehyde? Don't count these lone pairs. That's not your central atom. This is your central atom right here. And what you need to do is concentrate on the number of spokes coming out of that central atom. What we have is 1. This is 1. This is 2. This is 3. And that's because all you need to do is pay attention to that central atom. Don't worry about these electrons here. That's not your central atom. What you have is 3 regions around your central atom here. How about that? How many regions coming out of that? Again, don't pay attention to these lone pairs on nitrogen. Just think of this as your central atom, and what you have is 1, 2. 2 regions of electron density around that carbon. How about that? Well, you probably figured it out already. There's 2 regions of electron density. There's one region here, and there's a second region there. How about that? This is your central atom. Let's pay attention to the carbon. These are actually our central atoms as well, but let's not talk about that. Let's just talk about this carbon, and you can see there are 1, 2, 3 regions of electron density. Are you getting the hang of it? Well, let's take a look at this one. How many regions around that? If you said 3, you're wrong. What we have is 1 region, 2 region, 3 region, and remember, a lone pair is its own region, so this has 4 regions of electron density, or 4 spokes coming out of the nitrogen. How about that? That's ozone. How many regions? You should have gotten 3. This is 1, this is 2, and this is the third one, 3. Now why is that so important? Counting regions, this 2 has 3, is because once you know how many regions a structure has, that has 3, this has 4, 1, 2, 3, 4, okay? Once you know how many regions a structure has, then you can go here and use this chart. You can use this chart in your exam. You can use this chart for your homework and count. Where are we? Do we have 2 regions of electron density around the central atom? Do we have 3? Or do we have 4? And the only thing that we need to pay attention to is the regions of electron density, because once you know the regions of electron density around the central atom, you now know its electronic geometry. 2 will be a linear, 3 will be trigonoplanar, and 4 will be tetrahedral. It's that easy. You have to count spokes on a wheel, however. Okay? Now, let's do some examples. Let's consider cyanide, HCN, hydrogen cyanide. There's 2 regions, 1, 2. So we go to that chart, we're right here. So we can say that the electronic geometry, or the AE system's AE2, 1 central atom, right here, and 2 regions of electron density, right here and right here. That's why it's AE2. And then if we take a look at these 2 regions, what we have is, at the end of these regions are 2 bonded atoms. So that's why we go from AE2 to AB2, because there are 2 bonded atoms, no lone pairs around that central atom, so the molecular geometry is linear. It's got an ABE system of AB2. That's HCN. Another example would be carbon dioxide. If you take a look at the central atom, there's 1 region, 2 region. So we're here, it's linear in terms of its electronic geometry, it's AE2. And if we look at the molecular geometry, there are 2 atoms at the end of these regions, no lone pairs, no lone pairs. This would be lone pairs right here, LB, LP, okay. Non-bonded would be 0, and so we would have an AB2, it would also be linear. Let's take a look at ozone. This is in 2. This is 1, 2, three regions of electron density. So we're right here. We're right here. The electronic geometry would be trigonoplanar. This would be a trigonoplanar chemical. It's got three regions. But take a look at the bonded atoms. At the end of each region, there's two bonded atoms, and one lone pair. So the molecular geometry is bent, because when you look at this chemical right here, it's a bent structure. The ABE system would be AB2E. It's a bent structure. Let's take a look at another example here. Let's take a look at BH3. BH3 has three regions, and at the end of each region there's bonded atom. You guessed it. This should be a trigonal electronic geometry, and then three bonded atom, zero lone pairs. It's trigonal molecular geometry as well. So, counting spokes in a wheel, you can figure out the molecular geometry, which is in this column right here. But first you need to figure out how many spokes, which is right here, which gives you the electronic geometry. Once you count the number of bonded atoms each central atom contains, and take into consideration the lone pair, you've got the molecular geometry. Let's take a look at some more example. Let's consider that formaldehyde. Here you can see three regions. 1, 2, 3. We're right here. It's got a trigonoplanar electronic geometry. We've got three bonded atoms, zero lone pair on that central atom. We've got a trigonoplanar molecular geometry. It's that easy, really. You just need this chart. This right here is urea. If we look at the central atom right here, we can see there are 1, 2, 3 regions of electron density. There's actually two lone pairs on that oxygen, but that's not important for the molecular geometry. We're here in terms of the electronic geometry. We're here in terms of the molecular geometry. The molecular geometry of urea is trigonoplanar. We already did ozone. Let's take a look at this one. This chemical is NO2. Three regions of electron density. 1, 2, 3. We are here. Two bonded atoms, one lone pair. This structure, like ozone, is also bent. Let's take a look at the next one. This is methane. If you take a look at methane, there are four regions of electron density. Remember, you need the Lewis structure to do this exercise. If you don't have the right Lewis structure, you're not going to get this right. Four regions of electron density. This has four regions of electron density, but three bonded atoms, one lone pair. This has four regions of electron density, four bonded atoms, zero lone pair. And water, four regions of electron density, okay, two bonded atoms, two lone pairs. So all these three would be right here in red. Right here in red. For methane, you have 4 and 4. The regions of electron density will always give you the electronic geometry. All of these have tetrahedral electronic geometry, but they have differences in molecular geometry, whereas methane is tetrahedral because it's got 4 bonded atoms, a 0 lone pair. Ammonia is pyramidal. It's called pyramidal because it's got 3 bonded atoms and 1 lone pair right here. And then water is bent. We call this bent tetrahedral. Don't just say bent because there's 2 bent here. This would be a bent tetrahedral. This, however, is called a bent trigonal because it comes from a molecular geometry, it comes from an electronic geometry that's trigonal. This comes from a electronic geometry that's tetrahedral. So you have to state the difference. And remember, a pyramid is not a trigonal planar. This is a pyramid. It uses this third dimension. So this is your VSEPR table, and use this table to figure out the molecular geometry, the electronic geometry, and the bond angle around the central atoms. These are the bond angles around the central atoms, right here. Okay, you notice that the bond angle is tied to the electronic geometry. If you're linear, you've got a bond angle here that's about 180. If you're tetrahedral, you got a bond angle here that's about 120. 120. And if you're tetrahedral, you've got a bond angle here that it's about 109.5. If you want, you can go to ChemDL and you can look at the three-dimensional shape of these chemicals through a program. I was involved in this type of project in Washington, D.C. And let me just go to that particular site so that you can see. If you ever question the shape of a chemical, you can look it up. So let me go ahead and go to that site. Type in ChemDL. And in ChemDL, we're going to look at Model 360. And this is where you would find my tutorial on nomenclature, by the way. So that right there is, that chemical right there, I believe is your bromate ion. This is your bromate ion. See this bromate? It's actually a pyramidal shape. And you can see the shape right here as I rotate this. Okay, you can see that. So what you can do is you can go right here and type in the formula. Let's say I want the formula of ozone. Ozone. Type ozone, or I could type O3, and it should give me a drop-down menu on that structure. Maybe not. It gave me the wrong one. O3. No, you have to put the name ozone. Ozone is O3, and then we'll click on it, and you can see it's bent. It's a bent structure. If you go over here, you can take a look. You can make that chemical spin by clicking here. You can do a space filling model by clicking here. If I can control my mouse. You can figure out the bond angle right here. 117, which is close to about 120. It's not exactly. You can label the atoms. So go to ChemEdDL if you want to see the shapes of these chemicals. So let's go back. Let me show you these series of exercise right here. So this is, I believe this is caffeine. And the question is, this is a very complicated structure, but what is the molecular geometry around each of these central atoms? Keeping in mind that when you see an angle like this actually represents carbon right here. Okay, so that actually represents carbon. Let me draw that in. There's a carbon right here. It's another carbon right here. It's another carbon right here. Carbon right here. Okay, And then the next thing you need to do is you need to complete the Lewis structure. And remember, all these elements are in the second period, so it's going to be the octet rule. Oxygen has 4 bonds, I mean 2 bonds. It's already got 4 electrons here, it needs 2 more. That oxygen likewise needs 4 more electrons to give it an octet. That nitrogen has 6 electrons, it needs 2 more. This is just completing the octet. So that basically is the completion of the octet rule. Now we can figure out the molecular geometry around each of these atoms. And the way you do that is count spokes. This nitrogen has 1, 2, 3, 4. It's got 4 spokes, and it's got 3 bonded atoms, 1 lone pair. You're going to tell me that this nitrogen is going to be pyramidal shape. That's a pyramidal geometry. This carbon right here, it's got 1 region, 2 region, 3 region. That's trigonoplanar geometry. It's got 4 bonds. This carbon right here, it's got 1, 2, 3 regions of electron density, 4 bonds. That also is trigonoplanar. This nitrogen right here, it's got 1, 2, 3, 4. 3 of them are bonded atoms. 1 of them is lone pair. This is a pyramidal shape. So you can see that it's pretty straightforward to figure out the geometry around each atom if you just count the number of spokes around each central atom. So in summary, what we have here is we can determine the shape, the electronic geometry of a chemical. From the electronic geometry of a chemical, we can determine its molecular geometry using that VSEPR table. But it all comes from the Lewis structure. If we can't draw the Lewis structure correctly, we're not going to be able to count the spokes on the central atom, and we won't be able to get the electronic geometry, which won't give us the molecular geometry. So everything's dependent on each other. You need the valence electrons to get the Lewis structure. You need the Lewis structure to come up with the electronic geometry. You need the electronic geometry to come up with the molecular geometry. In the next section, you're going to use the molecular geometry to determine the polarity. So everything's related.